It's Algebra 2, Lesson 6.1, using properties of exponents. We're using properties of exponents to evaluate and simplify expressions involving powers. And we're using exponents in scientific notation to solve real-life problems. Beginning on page 323 in the textbook. There's a definition of scientific notation. Everyone in here is familiar with scientific notation. You just might have forgotten exactly the criteria that makes it up. The number has to be between 1 and 10, or it has to be at least 1. Notice it says 1 or is less than or equal to the number, which is less than 10. It cannot be 10. So it's got to think of the numbers between 1 and 10, counting 1, not counting 10. It's in the form C times 10 to the nth power. Okay, so it's always going to be times 10, to where you just move the decimal over one time. But the number that multiplies by that times 10 to whatever the power it is has to be between the numbers 1 and 10. N is an integer. N is not a fraction. It's not a partial number. Okay, so we have a handful, or a little more than a handful, of the properties of exponents. First one says let A and B be real numbers and M and N be integers. So we're not dealing with any fractions or decimals right now. The first one is the product of powers property. What you have to know about this one, when you have A and A, notice both of the bases are exactly the same. And then you have two different numbers that are the exponents, you add the exponents. It could be two different numbers or two of the same numbers. You still add them. What you need to know, though, is when you're talking about multiplication, it goes with addition. They're paired together. So when you have two numbers that are multiplying by each other, you add the exponents. When you're raising a power to a power, you multiply them. So when you're multiplying the numbers, you add the exponents. When you're raising a power to a power, you need to multiply them. The power of a product property, now you have two numbers inside of the parentheses. Those are multiplying and being raised to an exponent. It almost acts and looks like and feels like the distributive property. You have to distribute the power of M to A and to B. And notice that's what it says, A to the M power times B to the M power. It's not the distributive property, and it's wrong to call it that, but that's how most of us see it and think of it and keep it organized in our brain. A negative exponent. Another way to think of a negative exponent is called the elevator rule. Remember what elevators do. Elevators go up and down. Anytime something is being raised to a negative exponent, you need to ride the elevator with it. Right here, this says A to the negative M. Now, there's no fraction or anything. So what you need to do is mentally, you need to create a fraction by putting it over the only number you're allowed to put it over, which is 1. So now, the thing that's being raised to the negative exponent is A. It's being raised to a negative M. It needs to ride that elevator. This right here needs to ride that elevator and go down. Now, 0 is not left on top. You can't leave nothing on top, because if you would have 0 on the top, 0 divided by anything would be 0. So the only thing that's left on top is 1, simply as a placeholder. 1 over A, it goes down, and it raises, since it rode the elevator, it becomes positive M. Anytime you go from the top to the bottom or the bottom to the top, you switch the sign. In this case, you don't want to leave negative exponents, so when it goes down, it becomes a positive M. Anything raised to the 0 power is 1. The best explanation I've ever seen for this is this right here. 4 to the 3rd power, let's say 4 to the 4th power. 4 to the 4th power. What does that represent? Or what is that showing? And most of us, when we see something like that, we'll say, okay, that's 4 times itself 4 times. 4 times 4 times 4 times 4. So if that's the case, then 4 to the 3rd power must be 4 times itself 3 times. And it kind of starts looking like a little tree when you do this. 4 to the 2nd power is equal to 4 times itself 2 times. And then 4 to the 1st power, even though we don't write anything as to the 1st power, is 4 times itself 1 time. I don't think anybody in here would argue with what I have written up here. The one thing I'll add to this is what makes anything to the 0 power 1. All of these numbers, and if we look at that one, 4 to the 0 power, all of these numbers are correct. But there's one more thing that's added in. And the reason you don't write the one more thing that's added in is because most of the time there's no reason to write times 1. So 4 times 4 times 4 times 4 times 1, 4 times 4 times 4 times 1, 4 times 4 times 1, 4 times 1. So what's the only thing that's left over from that? There are no more zeros because it's to the 0 power. So if the tree just continues to go down, then it's simply 1. And that's why anything raised to the 0 power is 1. Now, that might not be the official real smart reason that that's why it's to the first power, but that's the, or it's 1. That's the only thing that ever made sense to me, why anything to the 0 power is 1. Most students just remember anytime they see something to the 0 power, it's 1. So right here, a to the 0 power is 1 when a is not the number 0. Quotient properties. Remember, up here, this first one, we said when things multiply, you add the exponents. Right here, we have division. A divided by A. This, again, the same base. You subtract the exponents. So anytime you have division, that is paired with subtraction. Division is paired with subtraction. Multiplication is paired with addition. Division with subtraction. And then the power of a quotient property says that a over b to the m power is the same thing as a to the m over b to the m. Earlier we had a fraction raised to the fifth power, or whatever it was, for the bell work, and we did 1/2 times itself 5 times. You can do that. A over b, we could do it times itself, however many the number m is. But again, just like this one here, where we said the product or the power of a product, we kind of treated it like the distributive property, and we rose a to the m and b to the m. You can do a to the m and b to the m, and it becomes a to the m over b to the m. So it's almost like you're distributing it to that as well. Again, that's not the official term to distribute, but that's how most of us think of it. So let's take a look at an example like that. 7 to the 6th power over 7 to the 3rd power. Again, the second to last property we just looked at was the quotient of properties, or the quotient of powers property. We said that multiplication went with addition. Right here we have division. So since multiplication goes with addition, what does division go with? Again, if multiplication is paired with addition, right here we have division. What is division paired with? Subtraction. So we have 7 to the 6th power over 7 to the 3rd. That's the same thing as 7 to the 6 minus 3, which is 7 to the 3rd power. This will be about the only step from here to here that you want to use a calculator on. You don't need 6 minus 3 in a calculator. But 7 to the 3rd power is 7 times itself, which is 343. B says 3 to the negative 2 power. Remember, anytime something is raised to a negative exponent, everything is over 1. It's got to ride the elevator. When it rides the elevator, this is what goes down since it is being raised to a negative exponent. So since that goes down, it's going to be 1 at the top over 3 squared. And that's what we have here, 1 over 3 squared, which is 1 over 3 squared means 3 times 3, which is 9. C says 3 squared squared. Remember, anytime you raise a power to a power, you multiply them. You don't add them right here. This is something that people make mistakes with all the time. With 2 and 2, it doesn't matter because multiplying them and adding them is going to come out to be the same thing. Multiplying bases add exponents. Power to power, multiply the exponents. In this case, 2 times 2 is 4. And 3 to the 4th power, again, that might be the one step you want to calculate it for, is 81. On the back, everybody, let's do these 3 problems. This one first. 3 to the 4th power squared. Take about 30 seconds. Again, refer back to your properties of exponents to know. Do you add these Do you multiply them? Do you divide? What do you do with them? Okay, let's take a look at this one. It's 3 to the 4th squared. You have to know raising a power to a power means 3 to the 4 times 2. This is one of those instances where you multiply them. That gives you 3 to the 8th power. We know that means 3 times itself 8 times. Again, this is the step where you might want a calculator. Instead of saying 3 times 3 times 3, instead of hitting it 8 times, in your calculator you can press 3 and you can hit that button that looks like this. That's called a caret button. 3 raised to the 8th power. And when you do that, you get 65, 61. So that's a power to a power. What about 5 over 8 to the 3rd power? Simplify this one. Again, use the same properties that we just used. Don't do 5 over 8 times 5 over 8 times 5 over 8. Use the properties we just did. Take about 30 seconds. Okay, we have 5 over 8 to the 3rd power. Again, to say 5 over 8 times 5 over 8 times 5 over 8 is not wrong. In fact, it's completely right. But a minute ago we said when you're raising something to a power like this, you can raise both 5 to the 3rd power and 8 to the 3rd power. This is going to make uh, the most sense when we're doing it with algebraic expressions. 5 to the 3rd power is 100, means 5 times 5 times 5, which is 125, and 8 to the 3rd power is 512. So 125 over 512. And in this one, negative 2 to the negative 3rd power times negative 2 to the 9th power. Take about 30 seconds on this one. Again, you have something being raised to a negative exponent. There is no fraction involved here, so we can create a fraction by putting everything over the number 1. What's being raised to a negative 3, in this case, negative exponent, is negative 2. This is being raised to the negative 3. So this has to ride the elevator down. So now what you're left with on the top is negative 2 to the 9th power. That's not being raised to a negative exponent. Even though it's negative 2, it's being raised to a positive 9. Over, it's still negative 2. And again, only because it's in parentheses does it go down. Negative 2 to the negative 3rd becomes the 3rd power. So now you have the same base, negative 2 over negative 2. And we have exponents to the 9th and to the 3rd. So when you have the same base, you subtract the exponents. Negative 2 to the 9 minus 3, or negative 2 to the 6th power. We know that this is an even amount of negatives, so it's going to be positive at the end. And 2 to the 6th power, earlier we did 2 to the 5th power and got 32. So 2 to the 6th power must be 64. Now there's another way to do this, and some of y'all might have looked at it and said, wait, why did you have to do all of that? Because I wanted to show the when you have division involved. What about if you just look at it all the way at the beginning as negative 2 to the negative third times negative 2 to the ninth? Both of those have the same exponent. Yes, they do. Or both of those have the same base, I should say. Yes, they do. So you might have said negative 2 to the negative 3 plus 9 and added the exponents. And when you did that, you would have got negative 2 to the positive 6, which is putting you right back at this step here. So two different ways to do it, still coming up to the same number, positive 64. Now here we're dealing with algebraic expressions. Now we don't have bases that are numbers, bases that are integers. We're dealing with variables. X to the negative third over y squared to the fourth. So just like a little while ago, anytime you're raising things inside parentheses to an exponent, this one's going to, both of them are going to get the fourth power. That one will, and that one will. Again, most of us think of that like the distributive property because you distribute it to that. So it's x to the negative 3 times 4. A power to a power means you multiply it. Negative 3 times 4. And y squared times 4. So x to the negative 3 times 4 is x to the negative 12. Y to the 2 times 4 is y to the 8th. You are not only in scientific notation, which we'll look at all the way at the end of this lesson, only in scientific notation are negative exponents acceptable. Right here we have negative 12. That is not acceptable. The way you change that is whatever is being raised to a negative value, it rides the elevator. This is the only thing being raised to a negative, so it has to ride the elevator. So there's nothing left on the top. You can't represent nothing with 0 when you do this because the whole thing will be 0. So we'll represent it with 1 at the top over x. Now it becomes to the positive 12 since it rode the elevator. Y didn't move at all. It stays right where it is. Y to the 8th. So 1 over x to the 12th, y to the 8th. B says negative 3a to the third, a to the ninth, a to the negative 7th. Again, inside parentheses is negative 3a. That's being raised to the third power. So both of those need to get raised to the third power. Negative 3 and a. Now, in this case, it's not just the number 3, since it's inside of the parentheses. This isn't 3 times 3 times 3. This is going to be negative 3 times negative 3 times negative 3. So when you do that, you have negative 3 to the third, a to the third, a to the ninth, a to the negative 7th. Negative 3 to the third, that's an odd amount, so it's going to become negative at the end. 3 times 3 is 9 times 3 is negative 27. Negative 27. Notice all of your A's as bases. A, and A. All of them are the same. So you add the exponents. 3 plus 9 minus 7. But you're thinking to yourself, wait, you just said to add the exponents. Why are you subtracting 7 there? Because adding a negative value is the same thing as what? As subtracting. Adding a negative is the same thing as subtracting. So don't let this confuse you with dividing and subtracting the numbers. We are not subtracting 7 because we're dividing. We're adding a negative 7, which is the same thing as subtracting. So 3 plus 9 is 12, minus 7 is going to be 5. So we have negative 27a to the 5th power. And there's nothing else we can do with that problem because we don't know a value of the variable a. C says c to the 4th d squared over c to the ninth d squared. Again, both terms are going to get squared since they're inside the parentheses. C to the fourth times 2 and d squared over c to the ninth d squared. C to the fourth times 2 is c to the eighth d squared. Now at this step, c is divided by c, same base. So division goes with subtraction. That's the same thing as c to the 8 minus 9. And d is dividing by d. That's, again, division goes with subtraction, d to the 2 minus 2. So that's what you'll have, 8 minus 9 and 2 minus 2. 8 minus 9 is negative 1. 2 minus 2 is 0. A minute ago we said anytime something's raised to the 0 power, it's the same thing as 1. So it's not d to the first power. It is 1. It's the whole thing becomes 1. This goes away and gives you 1. So you have c to the negative 1 power times 1. Again, nothing can stay with a negative exponent. So c to the negative 1 has to ride the elevator down. 1 remains at the top, and it goes down. C raises to the positive 1, and there's no reason to write a positive 1. So 1 over c. On the back, let's do these. Let's do them one at a time. The first one, a squared over b to the negative third to the third. Take about 30 seconds on this one. Again, all small numbers. You don't need calculators and none for any of this. Okay, again, everything in the parentheses is being raised to the third power. So this is being raised to the third power, a to the 2 times 3, and this is being raised to the third power, b to the negative 3 times 3. Remember, anytime you raise a power to a power, you multiply. So a to the 2 times 3 is a to the 6th power. B to the negative 3 times negative 3, opposite signs is going to be negative. 3 times 3 is 9. The problem with this, though, is you can't leave a negative 9 as an exponent. A to the 6th power doesn't need a move because it's totally fine to have a to a positive number, but this b to the negative 9th does have to move. It's got to ride the elevator and go up. So when it goes up, it becomes b to the positive 9th, and a to the positive 6 doesn't go anywhere. All of this would be over 1. There's no reason to write over 1. Oh, there's no reason to write over 1. So this is the simplified version. A to the 6th, b to the 9th. Let's take a look at another one. Again, these problems look long, but they're very easy. Negative y squared to the 5th, y squared, y to the negative 12th. Take 30 seconds on that one. Negative y squared to the 5th. Negative y squared is raised to the 5th, which means negative y squared to the 5th 2 times 5, which is going to be negative y to the 10th power. You still have y squared, y to the negative 12. Now, all of these have the same base, even though this looks different, because this is the same thing as negative 1 times y to the 10th. So all of these have the same basis. But to make sure we get it correct, let's simplify. Let's act for a second like this part of the problem doesn't exist. And you can always do this kind of stuff anytime you're not sure. Negative 1 y to the 10th, that's an even amount. So since it's an even amount, it's going to be a positive number at the end. So it's going to be y to the positive 10th. So you have y to the positive 10th times y squared times y to the negative 12th. Now they're the same base. All of them say y. So since they're all multiplying by each other, y times y times y, you add the exponents. 10 plus 2 minus 12. Again, I added that exponent negative 12. Minus and 12 is the same thing as adding a negative. So 10 plus 2 is 12, and 12 minus 12 is y to the 0 power, which everything we know to the 0 power is 1. So we have 1 as our simplified answer for that. And then finally, the last example problem, rs squared over rs to the negative 1 to the third. Take 30 seconds on that one. rs squared at the top is going to stay like it is for a second. Rs to the negative 1 to the third needs to be raised to the third power. That means this need to be raised to the third power, so r to the third, and this needs to be raised to the third power, s to the negative 1 times 3, which at the bottom will give you r to the third, s to the negative third. At the top, we still have rs squared. So right here, before we ride the elevator, not quite yet. Let's say that r to the first power is divided by r to the third power, which means r to the 1 minus 3. And s to the second power is dividing by s to the negative third power, which means minus a negative third. What happens when we minus a negative something? We know we need a plus a positive. So s to the 2 plus 3 is s to the fifth. R to the 1 minus 3 is r to the negative 2. So now we have one thing that needs to ride the elevator. You can't leave something with a negative exponent. This needs to go down. S to the fifth stays on top. R squared goes to the bottom. And that is your simplified version. And we'll pick up the rest of this tomorrow.